Hello, sir. This is the third video to explain the base case of IEEE 69 passes. As explained before, 33 network, it is the same thing. We have, as you see here, we have the file, the load file. Contain the number of paths. The first column, the second it is the real power, and the last one it is the reactive power, and also the specification of network, also the file of the line data. The first column it is the number of line, the second it is the sending in the bus, and the third one is the receiving in bus, and after that we have the resistance of each line and the reactance of each line, as you see here, and this is the rated power for the lines. After that, file the specification of the IEEE network in 69 passes. We go to the base case file. It is the main file that from here we can operate it or run the program. As you see here, it is a clear CLC, all the variables and the command window, and after that we call the line load file, load flow, and after that we get it the result from the load flow file or code, and then we printed the results. As you see here, after that we put the printed result like this. It is the power loss coming from the load flow, the reactive power loss, the voltage deviation, voltage stability index, and the last one it is the total system cost for the base case. And then we printed or plotted the voltage profile for each buses, and after that also the system profile, the load and the PV and the distributed generation and the grid, the power imported from the grid, and the other figures it is for the how the EV load and the losses behave. As you see, if you run, as you see here, printed the result, the power loss like this, and the reactive power loss, and the voltage deviation and voltage stability index, and the last one it is the total system cost in dollar. And if you see here, you can see the voltage profile for each buses. As you see here, this is the range of the voltage, the minimum voltage it is here, and the maximum voltage it is here, for each buses the voltage profile. And also we have figures, figure for the system profile, the system load, how the system load behave, as you see here, and how the generation from the PV and the generation from the distributed generation, how to behave, and follow up the load. And the last one it is the grid, also how to import the energy from the grid. This is the system profile, generation profile. The last figure for that it is the EV load, how the EV load, as you see here, and how the losses behave with the EV load. As you see here, it is compatible between the EV load and the losses of the system. This is the explain of the main program. But the last file it is the load flow. As you see here, the initial parameter, accumulated power loss, reactive power. This is initial parameters, and the hourly load of the load profile, and call the load data and bus data specification of network, and after that the PV generation price, how much, and also the grid import price. And after that preparing the data dependent on each reading datas and the profiles, and initial some network parameter like the base MVA and the base voltage and base impedance, and after that we calculated the per unit value of the resistance and reactance for each line, and then after that we applied the profile, as you see here, the real power profile and reactive power profile, and also replace or locate the PV and distributed generation for the generation, and the electric vehicles also located in each bus that we put it in the specification of the project. And after that we started the load flow, as you see here. The load flow, the first thing it is to arrange the buses as a radial arrange, and after that also define the path of each from the source to the load, and determine how much the path and how the bus connected with each other. This is code, it is from line 50 to line 174. And after that, after arrange that as a radial network, then we started to calculate the voltage current program by using feed forward back propagation. So in the first we assume that all buses voltage it is 1, and after that we repeated in loop to calculate the current. The first thing it is to calculate the current dependent on the assumed voltage and the real and reactive power on each buses, and after that we calculated here the accumulated branch current that current flow in each line. And after we calculated the branches, the accumulated current branch current, so after that we back to calculated the voltage of each buses depending on the branch current, and after that we repeated this process 5 times, and then we extract the voltage values and angle, and also we calculated the losses, the power loss, reactive power loss, voltage stability index, and the voltage deviation, as you see here, from dependent on the voltage and the power flow in each line. And then after that we divided this power loss on the number of hours to calculate the average of the power loss, reactive power loss, voltage profile, voltage division, and voltage stability index. And then we calculated the total system cost dependent on the PV generation, dependent on the grid generation, and also dependent on the load from the distributed generation. So after that this power loss and the reactive power, voltage division, and voltage stability index, and total system cost, it is as a output, and back to the main program to print the result here. The last file, it is the profile, as you see here. In the base case we assume that is the profile, the real power, real load and reactive load profile, and then the PV generation in the 4th column, and 5th one it is the distributed generation 1, and the next one it is distributed generation 2, and the next one it is the AV profile, and the last one it is the distributed generation cost for each hours. That's it for the IEEE 9069 buses base case. We hope it is clear for you, and if you have any question you can ask us, and we will help you to clear the idea more and more. And thank you very much for your listening. Goodbye.